Hi, welcome to S Mathematics. In this video, I have given the title as Problems Abelian Groups, Group Theory Part 4. In Part 3 and 3a, I concentrated much on composition tables with finite groups. Part 3, finite group with respect to ordinary addition and multiplication. In Part 3a, I concentrated finite groups with respect to addition modulo and multiplication modulo problems. Here also I am concentrating finite groups. See, groups are very important tools in order to make the student to able to understand the concept of group very well. I am giving more examples in 4 videos. Altogether I am giving 25 examples or 24 examples I am giving. Now see the example here. Now the problem is prove that all groups of order 4 and less are commutative. What do you mean by order of a group? The number of elements in the group is said to be order of group. It is denoted by O of G or modulus of G. Order of group is this. Now what you have to prove? All groups of order 4 and less are commutative. That means what you will get? Order of group G is equal to 1, is equal to 2, is equal to 3 and 4. Now what you are going to do? You are going to take a group with one element. You are saying that it is an abelian group. A group with 2 elements, you are saying the elements may be any elements. But they said any group which is having less than 2 elements will be abelian. Less than or equal to 4 will be abelian. Now you will take first order of G is equal to 1. When order of G is equal to 1 means the group which is containing only one element means it is a group which consists of only the identity element E. This is the G. G is equal to E. E dot E or 0 plus 0. If it is with respect to plus E plus E, E is equal to E. Then where is this is E. E dot E is equal to E. This G is commutative. You can say that. Next, suppose order of G is equal to 2. It is having 2 elements E. E dot E is equal to E. E dot A is equal to A dot A is equal to A, and A dot A is also should be E. See how it is. It is commutative group. Now using the composition table also you can say. Now this is E A dot E A. This will be the composition dot. See here. E dot E is E. E dot A is A. A dot E is equal to A. See here. A dot A, you should have to write, A dot A is equal to A, this is. A dot A is equal to E, you have to write. Because by the properties of composition table, in every row, the elements of the group must exist only once. There should not be the repetition in the composition table. That thing you have to remind. Therefore, this is a commutative group. See, all the elements or entries are in G and they are symmetric about the diagonal. E, commutative group. So, A is the inverse of A. Is it clear? Now, next, a group of order G. If you take order G is equal to 3. Order of G is equal to 3. Then how many elements G is having? E, A, B. Now this also with the composition table, if you say, it will be easy. Now take it. E, A and B. Now this is the table. E, A and B. This is the, see here. Dot. E dot E is E. E dot A is A. E dot B is B. Similarly, A dot E is A. B dot E is B. This you have to take. Write it first. Next, what you have to write? A dot A, either it is equal, because this is the row, A is already existing, A dot A, either this should be equal to E or this should be equal to B. That only heredity here. E dot E is equal to E, E dot A dot E is equal to A, E dot B dot E is equal to B. That you have written already. Now, AB is equal to A, suppose. Then AB is equal to AE. Is it? Can I write? AE you can write. By cancellation, A will be cancelled, B is equal to E becoming. Is it possible? Because E, A, B are the distinct elements, because order of G is 3. So, B is equal to E, which is not possible. Similarly, if AB is equal to B, then AB is equal to EB, then A is equal to E. Then it is also possible. Not possible. Therefore, what you have to take? AB is equal to E, A square is equal to, now see here. Here you have to write AB is equal to E, A square is equal to B, and B, A is already there, E, A. Now this is the composition table, okay. Therefore, you can say that order of G is here also the same. E, A, B, see A is equal to E, it is not true. Therefore, A is equal to B, B is equal to A, you have to take. The composition table is like that. E, A, B is B, A dot B is E, B dot A is E, B dot B is equal to A. Is it clear? Now, if you see the composition table here, this is the body of the table. From the body of the table, you can observe all the entries belong to G. So, closure satisfies, and identity in each row, identity is existing in each row and each column. So, identity exists, and E is the inverse of E, A is the inverse of B, B is the inverse of A. And if you take the principal diagonal, these elements are arranged in symmetric way. Therefore, your abelian property satisfies. Next, order of G is equal to 4. Let G is equal to E, A, B, C. Here, every element in G has inverse in G. Then there arises 3 cases. Now see, there are 4 elements. You can write the composition table. See how we are going to write. Now, every element has inverse. That means A is the inverse of A, B is the inverse of B, C is the inverse of C, E is the inverse of. That is the first case. Every element has a self-inverse. We have proved one problem in 3 or in the set of 3 or in video 3 or video 3a, I didn't remember. But every element has its own inverse, means that group will become an abelian group. In such a case, it is okay. Next one, second case. Suppose A inverse is equal to A, B inverse is C, C inverse is equal to B. Suppose every element in G has self-inverse, then it is commutative. Already I told you, similar here also proved. Now second case C we will prove. Case 2. A inverse is equal to A, B inverse is C, C inverse. Now E dot E is E. E dot A dot A is equal to A. E dot B dot E is equal to B. E dot C dot E is equal to C. Now if AB is equal to B, what happens? See. If AB is equal to B, as in the previous case, you are getting A is equal to E, because B can be written as EB. By left cancellation law or right cancellation law, you can cancel A is equal to BA. Similarly, if BA is equal to A, you will get this. Therefore, you have to take AB is not equal to A, B, or BA is not equal to A. Therefore, you have to take AB is equal to C, C is equal to BA. Similarly, AC is equal to B, B is equal to CA. Therefore, AA is equal to E. Now, see the composition table. Now, similarly, AC is equal to B is equal to CA, AA is equal to E. BB is equal to B implies B is equal to E, which is not true. Similarly, BB is equal to AB, C is ABC, BC is equal to CB is equal to E, CC is equal to A. Using that, if you take the composition, see here, EABC, EABC. The first row, first column you can easily fill, because E is the identity you can take. Now, in order to fill the second row, see here, here if you take A dot A is equal to A is repeated. Okay, so you take E. After that, if you write here A dot B is equal to B is repeated. So you should not write B. Therefore, you have to write C. Similarly, A dot C is equal to B. The remaining element you have to write. Is it clear? Now see here. Already you got E and A. Here suppose B dot E is B written. Here B dot A if you write, this is either A or C. The elements are repeated. So you should not write either A or B. You have to write C. Here also, here you are having BC, here you are having BC, and the A you have to write. Here it is E. Now similarly C, B, E, A. Now if you observe the table, you can say that it is the abelian group. You will get 2-3 possibilities, but all the 2-3 possibilities will come, you will get only this table. Therefore, order of group less than or equal to 4, then it is an abelian group. Okay? Now, see the next problem. This is one of the problem. Now, you have seen cube roots of unity will form an abelian group. Cube roots of fourth roots of unity will form an abelian group. In composition table, you have seen those two problems. Here, nth roots of unity will form a group with respect to multiplication. Nth roots of unity can be written as 1 power n is equal to cos 0 plus I sin 0 1 by n. This is cos 2k pi by n plus I sin 2k by n. This can be written as e power 2k pi I by n. This is e power 2k pi I by n. Okay. Now this is also the same. Now omega is equal to that. If you take k is equal to 0 to n minus 1, that is n values you are taking, nth roots of unity. They are denoted by 1 omega, omega square, etc. omega power n minus 1, where omega is equal to 2 pi I by n. Now clearly here G is non-empty. G is non-empty. Now see here. Closure property. Suppose if you take, what is the set you have considered? Set is, you have taken the set as 1 omega, omega square and so on, omega power n minus 1. This is the set. Now in order to verify the closure property, take two elements from this. That is, you are taking w power r and w power s, a and b. A dot b is w power r dot w power s. W power r plus s belongs to G, because r plus s belongs to Z. R is an integer, s is an integer, Z plus is abelian group, therefore r plus s belongs to Z. Therefore, dot is a binary operation. Next, associativity. Associate, since the elements of G are complex numbers, they are complex numbers. You know, the set of all complex numbers will form a group with respect to multiplication, non-zero complex numbers. Therefore, it is associativity follows from the set of complex numbers. Next, identity. Clearly 1 belongs to G and a dot into 1 is equal to 1 dot into a is equal to a. Therefore, 1 is the identity in G. The first element you have taken it as 1. Is it? So, that will be the identity. Now, identity exists, closure satisfies and associativity satisfies. Since what are the left? Inverse is left. Inverse, let A belongs to G, A is equal to 1, then A dot A is 1 into 1, 1 is the inverse of 1, then it is okay. Now if A is not equal to 1, take A is equal to W power R and B is equal, that is omega power R, B is equal to omega power n minus R, that also belongs to G. Now A dot B is equal to omega power R into omega power n minus R, this is omega power n is equal to 1. A dot B is equal to B dot A. Therefore, omega power n minus R is the inverse of omega power R. Therefore, for every element inverse exists. Similarly, verify commutative. A comma B belongs to G. A is omega power R, B is omega power R. A dot B is omega power R plus S. That is nothing but S plus R. that is omega power s dot omega power r b dot a. Therefore, G dot is infinite abelian group. G is an abelian group. Okay. Now, is it clear? Next, this is also infinite group with respect to usual multiplication. Here, these are the powers of 2. 1, 2, 2 square, 2 cube, 2 power minus 1, 2 power minus 2, 2 power minus 3. This is an infinite set with geometric progression. I can say that it is 2. This is an abelian group under usual multiplication. It is very easy to verify. Now, first one, A, B, C belongs to G. A is 2 power P, B is 2 power Q, C is 2 power R in general you can take. P, Q, R are in Z. Now, first verify closure property. Take A dot B, that is 2 power P into 2 power Q, that is nothing but 2 power P plus Q. It belongs to Z because P is an integer, Q is an integer, P plus Q an integer, 2 power P plus Q belongs to J. Similarly, associative also you can see. 2 power P into 2 power Q, 2 power R. Now, this is 2 power P plus Q plus R you will get in general. Now, you can arrange because P, Q are associative in G where they are belonging to Z. Z plus is abelian. Therefore, in among P, Q, R, you can write P plus Q plus R. Associativity satisfies with respect to addition. That is 2 power P plus Q into 2 power R. 2 power P plus Q is nothing but 2 power P into 2 power Q into 2 power R. 2 power P is A, B, A dot B, C dot C. Now, is it okay? You have taken A dot B dot C, that is A dot B dot C. Next, if you take 2 power 0, 1 belongs to G. A into 1, 2 power P into 2 power 0 is 2 power P plus 0, that is 2 power P. So, A into 1, 1 into A is equal to A. 1 is the identity element in G. Okay? 1 is the identity element in G. Next, A belongs to G. A inverse belongs to G. We have to show that. Now, A inverse is nothing but 2 power P whole inverse. Consider A into A inverse. So, 2 power P into 2 power P whole inverse is 2 power P into 2 power minus P, that is 2 power P minus P, that is 2 power 0 is equal to 1. A inverse into A, that is 2P whole power minus 1 into 2 power P. The theory of indices you can write 2 power minus P, 2 power P. From this 2 power minus P plus P, that is 2 power 0 is equal to 1. Therefore, there exists inverse for every element A in G. Next, commutativity. Let A comma B belongs to G. A dot B is 2 power P into 2 power Q, that is equal to 2 power P plus Q. This is equal to 2 power Q plus P. This is 2 power Q into 2 power P, which is equal to B dot A. So, A dot B is equal to B dot A. Commutative property satisfies. That means all the properties, closure, associativity, existence of identity, existence of inverse and commutativity, 5 properties are satisfied with respect to the defined operator dot. Therefore, this will form a group. Okay. Now, see all these problems in similar way we will prove, but the operator is changing, that you have to find out. Okay. Now, see here. X is equal to 2 power A into 3 power B, and A comma B belongs to Z is a group under multiplication. Okay. Now, with respect to multiplication you have to see. Suppose X is equal to 2 power P 3 power Q, Y is equal to 2 power R 3 power S, Z is equal to 2 power L 3 power M, where P, Q, R, S, L, M all are belonging to Z. These are all the elements of Z. Z means set of integers. Okay. Now, let xy belongs to G. X into y. X is 2 power P, 3 power Q, 2 power R. So, this will be 2 power P into 2 power R is 2 power P plus R. 3 power Q into 3 power S is 3 power Q plus S, that belongs to G. Next, associativity. In the same way, you can show that. 2 power P into 3 power Q, 2 power R, 3 power S, 2 power L, 2 power M. Now, all the powers of t add. That is 2 power p plus r plus l, 3 power q plus s plus m. But what are p, r, l, s, q? All these are elements of Z. Z plus is an abelian group. Therefore, you can arrange them like this and you can write it as xy into Z. Therefore, associativity satisfies. Now see, identity. Let for all x is equal to 2 power q into 3 power q. Element 1 you can take it as 2 power 0 into 3 power 0. So, x into 1, 2 power p into 3 power q is equal to x. 1 means 2 power 0 into 3 power 0. Therefore, identity exists. Can I write to anything to the power 0 is 1. So, you can write 1. Inverse 2 power p into 3 power q into 2 power minus p into 3 power minus q, because pq belongs to z. For p, z plus is abelian with respect to addition. Minus p and minus q will exist in z. Therefore, you can take 2 power minus p, 3 power minus q, and x inverse is equal to, you will get it is equal to 1. 2 power p into 3 power q into 2 power minus p into 3 power minus q. You will get it is equal to 1. Similarly, x inverse x. Therefore, it is a abelian group. It is a group. Okay. Now, see here the next problem. Now, till now, with respect to multiplication you have seen. Now, with respect to addition, see here, this is also multiplication. See here, prove that the C naught of all non-zero complex numbers. See, you are taking C naught. C naught is nothing but C minus singleton 0. That is, from the complex numbers, 0 you are removing. 0 is a complex number. Will you accept 0 can be written as 0 plus I 0. With respect to addition, it is a group, we said already. Now, you are saying with respect to multiplication, it is a group. Now, because 0 is not having inverse, you are removing 0 from the set, and that set is forming a group with respect to multiplication, you are saying, is it? Now, see here. Prove that the set C naught of all non-zero complex numbers forms an infinite abelian group. C naught is A plus IB, where A comma B belongs to R. A, B are not both equal to 0. If one of them is equal to 0, if A is equal to 0, it will be only imaginary number. If B is 0, it will be real number. That's why A and B are not equal to 0 you have taken. Now, similarly here, A1 plus IB1 is x, y is A2 plus IB2, z is equal to A3 plus IB3. A1, B1, A2, B2 are A3, B3. All are where? They are all real numbers. Good, remember, these are all real numbers, belongs to R. Let xy belongs to C naught. So, x into y is A1 plus IB1 into A2 plus IB2. If you multiply this, A1 A2, IB1 A2, this term, IB1 A2, this term. Next, I square B2, I square B1 B2, I square is minus 1, this term. Next one is I B1 A2, I B2 A1. This is the term you got. Now, A1 A2 minus B1 B2 being this will be a real number. A1 B2 plus A2 B1 will also be a real number. Therefore, xy belongs to C naught. So, closure property satisfies. Similarly, associativity property satisfies in C naught because that is the set of complex numbers follows associative property. So, here also it will follow the associativity follows. Next, let x is equal to C naught. 1 can be written as 1 plus I0, that belongs to C naught. Therefore, x dot into 1, A1 plus IB1 into 1 plus I0 is nothing but A1 plus IB1, that is equal to x, and 1 into x is equal to A1 plus IB1, that is equal to x. Therefore, 1 is the identity element. Similarly, x is equal to a plus IB1. X inverse will be what? Now you have to find out x inverse. In order to find out the x inverse, now you will write this as 1 by a plus IB into a minus IB by a minus IB. There is nothing change, is it? So, therefore, a minus IB by a square plus b square, product of these two, belongs to C naught. Now, take x inverse. That means you are assuming this is inverse. This element as inverse. A plus IB into a minus IB by a square plus b square. That is nothing but 1 plus I0. This is a plus IB into a minus IB is a square plus b square. A square plus b square by a square plus b square is 1. That I can write as 1 plus I0. Therefore, x inverse is equal to 1. Similarly, x inverse x is also equal to 1. Therefore, x inverse is the inverse element of x in C naught. So, identity exists, inverse exists. Xy is equal to yx also satisfies. A1 plus IB1 into A2 plus IB2, that is A1 A2 minus B1 B2 plus I into A1 B2 plus A2 B1, that is A2 A1 minus B2 B1 plus I into, this is nothing but y dot x. Therefore, xy is equal to yx. All the properties are satisfied. Therefore, C dot is an abelian group. Now, see this also. Prove that the set of Q naught of all non-zero rational numbers forms a group under usual multiplication. This also is very simple. Let A comma B, Q naught means Q minus singleton 0. Now, Q minus singleton. A comma B belongs to Q naught means product of two rational numbers is again rational number. Associativity follows. Next, identity. Take it as 1. 1 is the rational number, 1 is the identity. A belongs to Q naught, A dot 1 into 1 dot A is equal to A, 1 is the identity. Similarly, if you take A, 1 by A will be the inverse. So, A dot B is equal to 1 implies B is equal to 1 by A. 1 by A is the inverse of A in Q naught. Therefore, Q naught is a group. Okay. Now, with this we are going to stop. Thank you.